Good evening, and welcome back to Vegas October 1 Sounds. A couple of little corrections to the last video. One is that a nanometer is really 1 by 10 to the minus ninth meters, or 1 billionth of a meter. I think I called it minus 12 or minus 15, which is entirely wrong. Also, when we left off, I was talking about how the muzzle blast is somewhat directional. And because of that phenomena, if you're either far to the left or far to the right, or at great angles to the muzzle of a gun, then the sound that you hear and or record is quite often vastly reduced in intensity and somewhat modified in the curvature of the wave. And because of that, it is pretty easy to hear a sound at those locations that is so different than what you're used to seeing from the gun that you actually classify it as a different gun. So for all the gunshot acoustic enthusiasts, beware of that. Also, I didn't do a very good job in the last video of explaining the relationship between wavelength, velocity of the medium, and frequency. So pop on over to Wikipedia, and here it is. So for a given fixed velocity v and a frequency f, you can determine the wavelength by taking the velocity and dividing by the frequency. So, for example, in air, with a velocity of 434 meters per second at a frequency of 1000 hertz, 1 over 1000 is 0.001 or 1 millisecond, times 343 meters per second will get you 0.343 meters, and that would be the wavelength for a frequency of 1000 hertz at sea level and room temperature. Alright, that out of the way, let's get back to the topic of this evening's broadcast, namely wave interference. What happens when you have more than one source of sound? Well, let's just start right off with sound and forget the water as an example. Here we have two speakers. Now let's put them at minimum separation. So here we're talking about a separation of 100 centimeters, and recall that there are 2.54 centimeters to the inch. So in this case, if we have a separation of 100 meters, what would that be? 40 inches, I think. Let's see, 100 centimeters slash 2.54 equals, 40 inches. So that's where these at, and we'll go up to 4 times that, or 160 inches. Alright, so let's go ahead and enable these speakers. It's already running down there. And we notice with the one speaker get going, amplitude's way up. Let's change the frequency to the minimum, which is probably around 100 hertz. And we notice we get these nice concentric circles that we're used to, with the white region representing a high pressure zone and the dark region being a low pressure zone. And if we put on the particle on top of the waves, you can see the little particles beating around there. Alright, but let's go back to waves, because it's going to get a little complicated here, and enable the second speaker with the same exact frequency of sound broadcast at the same exact time. What happens? Well, the wave comes out in a high pressure zone or low pressure zone, travels some direction, and meets up with its twin from the other speaker. And where the high pressure zones meet, they become a higher pressure. Where the low pressure zones meet, they become a low pressure. But when you have a high pressure meeting a low pressure, they tend to cancel out, and you get a much lower sound. And if we bring our little trusty dusty measuring gadget here and place it in the middle, we'll see the typical pattern of oscillating high to low. And if we bring another version over here into this little region where there's wave cancellation, and you'll see that the amplitude of the wave is much reduced, and it's still the same frequency, still the same cyclic rate, but it's much reduced, and we could better align those so that they arrive at the same time. Alright, now so at this low frequency, it still kind of sort of looks like concentric waves, but as we increase the frequency, let's say up to about 500 hertz, then all of a sudden we see something different. Now let's use the white one. What we see now is that the screen is divided in 3 very distinct zones. One in the middle, one on the top, one on the bottom. And in between each is this zone of small amplitude sound. And if we deviate from that zone a little bit, then we pop up into a region where once again we get the typical high and low pressure zones in the frequency that we've selected. Okay. Now, there's one other thing, and there's 2 of those gray zones, as I call them, or what do you call it, dead zones. Now imagine being at a concert where they have 2 speakers arranged like this, and you happen to end up in that region of deadness. It would be a very poor experience indeed, because no matter how high they were or how low they were to set the speakers, you would never be satisfied if you or your neighbor 5 feet to the left or right was satisfied. One would be receiving high and you'd be receiving low. And if they cranked it up high enough for you to hear, then the other people would probably be going deaf or bleeding at the ears. So this is what happens when you have 2 sources of sound identical in nature broadcast at the same time, but the sources of sound are separated, in this case, along the plane that's parallel to the Earth. And you can say, whoa, wait a minute, well then how do they arrange these things on stages? Well, what typically happens is you can select, since these speakers are on the stage, if we broaden the separation between them, which you'll see that the interference pattern now produces something quite different, which is now a checkerboard. So separating them didn't help. In fact, it worsened it, because now approximately half the people are receiving, well, that's not really true. The number of gray areas now has increased dramatically, so there's going to be a greater portion of your audience that is no longer satisfied with the quality of the sound. And if we drop back to the lower separation, I forgot to mention something. And that is, you'll notice that these sounds are no longer arriving at the same time. Directly in front of the distance between the 2 speakers, those sounds arrive first, but if you go off to the sides, they arrive a little bit later. So there's an actual delay in sound. And as you increase the separation and get the checkerboard pattern, you have that same phenomena, only there's more opportunity for it to be out of sync. Alright, so increasing the separation didn't help. What about frequency wise? Let's see what happens when the frequency, so back to the close position, and we increase the frequency, and as you can see, increase in the frequency now only really changes the little bit here in the number of these. Let's see. And if we increase both the separation and the frequency, or the frequency of the separation, then we probably have the worst of both worlds. Alright, so what happens? Let's go down to a low separation. Since you can see that there are high and low and dead regions here, and if you were out in the audience, you could walk from left to right of the stage and you'd run across these various regions. So left to right is bad, because that's a bad experience. So what they typically do is they stack these speakers on top of one another, bringing them as close together as possible. Alright, and then this phenomena occurs up and down. And since people's heads are predominantly fixed at one height or within the height of one region, then that pretty much eliminates their experiencing this dead zone or the delay. And that's how you do it. You stack them on top of one another. Now, if you get too many stacked on top of one another, there's still the opportunity for somebody to be in one of those dead zones. And then you only broadcast one channel of sound through that. And so let's presume that there's 10 speakers on top of each one of these, and you separate them out. And what will happen is that on one of the towers, as they call them, you'll broadcast, say, the basses. And on the other tower, you'll broadcast the vocals. And you'll put speakers at various locations to try to reinforce those and make sure there's a good quality of sound. So, back in the days of, all the big band, well, I don't know if I could say that, but anyway, there was, the Tower of Power, and that's precisely what they did, is they put massive amounts of power into this, vertically stacked speaker arrangement to try to eliminate this phenomena, and then only broadcast one channel through anything. Didn't try to broadcast the same channel through two different towers, unless they wanted the effect. All right. So as you can see, there's a lot going on here. This is called interference. So, what does this mean for other phenomena? Well, imagine trying to fake a gunshot sound by using speakers. If you were to have, people, I point out to people all the time that the timing of the gunshot sounds, particularly the supersonic crack, is position dependent. And because it's position dependent, you can't simulate it with the speaker, because whatever the speaker broadcasts, everybody hears the same sound, like in this. No matter what you broadcast over that, everybody's going to hear the same sound. But with real gunshots, as you move from one location to the other, you hear different timing between the supersonic crack and the muzzle blast. And some people have tried to say, well, they'll just use multiple speakers. But as I've just shown, that complicates the problem. All it does is muddy up the issue. And the more speakers you add, the more unclear it becomes. So, in reality, there's no good way to simulate gunshot acoustics with speakers, nor LRADs, nor anything else, unless you're using a truly holographic system, which, to my knowledge, does not exist today. Alright, so that's interference. What else do we want to say about interference? Well, this was just two sources of sound. Rather than speakers, let's talk about the frequency. Normal sounds that we hear aren't coherent as we have here. They aren't of the same frequency, same amplitude, and same timing. They vary in, each, second of sound contains multiple amplitudes and multiple frequencies. So imagine having 10 of these checkerboard patterns, none of them aligning, all overlapped into one region. Quite the mess, huh? And so you can see where what's happening out in the field of these interference patterns becomes very complicated very quickly. And that's why people get paid pretty good dollars to design, engineer, build, and set up the sound systems, because it's not just a straight line of sight thing where you can do a good job or just set your speaker at any place. And it is precisely these types of things where in a room where you have the sound coming from a speaker hitting a reflective surface, coming back and interfering with itself, that produce the nuances associated with every room. And again, there's big dollars in knowing what to do with that. Now, a lot of this has been automated in today's modern speaker systems, but there's still a great art there, a very great art to making sound good. And of course, as we all understand, a live experience is far different than a recording experience. Simply, once again, because of all the nuances of these types of wave interferences. Let's see, what else would I like to say about interference? The sources of interference. Not only can these interference happen because of two sources of speakers, for example, but you can have one speaker and a reflection. You can have two speakers and multiple reflections. But if you draw the analogy out to gunshot sounds, let's say you talk about the muzzle blast. Well, the muzzle blast event produces one type of sound that propagates as an ever-growing sphere. But that sphere interacts with the ground, with buildings, with people, with walls. And each time it does, there's the potential for absorption, reflection, bending around objects. And when you do, you change the time of arrivals of the sound such that when they meet back up, let's say you're bending around a light pole, and one wave comes around one side and another wave comes around the other side, and depending and where they meet, there is going to be this type of stuff, interference. And so the sound behind the pole in some region becomes a little squirrely, shall we say. It eventually kind of evens out depending upon the frequency. But if you have a reflection, commonly called, or an echo or reverberation or anything like that, then you could see where it would easily end up where the reflection could meet the original signal, only delayed, and you could end up with lots and lots of these different types of interferences, ending up with quite a unique and varied and distinct type of sound for each location that you're at. And so sound, particularly gunshot sound, is not just you look at it and you think that you have line of sight, but it's all the things that are around that interact with the sound that's being broadcast, which what was commonly called the soundscape, which is all the reflections and reverberations and noises from other sources, the entire soundscape. And that's unique to every location. So no two people hear or record the sound, even if it's the same sound event, the same. Period. Now, sure, they're quite similar in nature, and you can look at them and say, yeah, that's the same signal, but one's going to be louder, one might be delayed in time, one might be frequency modified, and things like that. So, all right. So that's it for this evening, and we'll grab you in the next one.